So here we have a free swing pendulum that we're trying to balance upside down. So we're using a rotor over here. There's a motor connected to the rotor over here. And we're using a sensor from the rotor and the angle of the pendulum to control the motor that connects to the rotor, which balances the pendulum and determines the position of the rotor. So we use these two sensors in Simulink to take the derivatives of each of the Q1, the angle of the rotor, and Q2, the angle of the pendulum, to derive our four state variables.
Okay, so the robot swings up, and now it's oscillating at 1.5 radians per second between pi over 8 and pi over 4 and negative pi over 4. Now we're going to show that it can also handle balancing a Sprint 2008 cell phone. So it's happy robot. So it's pretty stable. So right now we're giving a pretty big signal input to go to different positions as far as the rotor angle, but it still will balance the pendulum at its first rate. And then if we hit it hard enough, it just goes down, and it waits till it's slow enough to be stable, and then it does swing up again. And every time it goes back into swing up mode, we give it a gain of, we multiply the gain by 3 to swing up faster. Another thing we've done is make it so that, so you can see how right now it accelerates so that the rotor gets under the pendulum so that the pendulum doesn't fall. And if we made it go into the mode where, or if we didn't turn that off, once it got to an angle like this, it would just spin in circles to try to get under it, even though it can't reach a velocity that's high enough to actually catch the pendulum, and that would hit things and hurt people and make people cry. So instead we set it so that once the angle gets past 165, you can see right there, it's now turned off, and it goes to an input of 0 until the pendulum slows down enough for it to stably swing it back up. So, and so you can see how even though we're giving it an angle, a desired angle input, if the pendulum is going to fall, the robot will move so that the pendulum doesn't fall, because that's the highest gain.
Alright, this is a system for invert pendulum balance. So this here is a motor, the system of the robot. So it has a read encoder for motor and the pendulum, and the right analog to give our input our desired voltage. And here, this loop explains a PD controller for the motor. And this loop is a PD controller for our pendulum, which gives our desired angle for the system. So this is a subsystem for our timer, and here we have a function for starter and multiplier, and this takes time value and gives the initial voltage for a time less than 0.25 seconds, and this function gives a multiplier which multiplies the first few 1 or 2 swings with 3 times the voltage. Okay, so this function gives a condition for switching our swing up mode to balance mode. So once the angle reaches plus minus 165 degrees, the system will turn off. And when the angle is within plus minus 10 degrees, then the system will turn on again. And once the system is turned off, the system will switch back into the balance mode.
So the other part of the control system that we built was for the balance mode. So once the swing up is complete and it gets to plus or minus 165 degrees, the angle of the pendulum, the swing up mode gets switched off, and we turn on the balance mode, which in order to derive that control system, which is shown up here, we made a state space model and linearized it around the vertical pendulum position as angles Q1 equals 0 and Q2 equals 0. And so you can see for this control system, we take Q1, which is the angle of the rotor, and we take Q2, and then we also take the derivative, so the joint velocities, and we once we had the linearized state space version, we calculated the gains, which we multiply each state by, in order to get our voltage input that will control and balance the pendulum. So we set our poles for that at about -5, and all of them on top of each other, or almost on top of each other, so that we had a critically damped system, or as close to a critically damped system as we could have. So for the state space control, when we set those poles, these gains right here are the ones that were calculated, and so the first gain corresponds with the angle of the rotor. The second one is the velocity of the rotor angle, or the angular velocity, and then the third gain, which is the greatest one, is the angle of the pendulum, and then we have the angular velocity of the pendulum. And so, since the greatest gain is on the angle of the pendulum, that's kind of the first priority for the control, and it has that angle will have the strongest effect on the system response. So then the other part that we had to develop for the balance control was the switch off. So at first we were having problems because once it got past 165, it would immediately be in swing up mode. So what we've done is, even though swing up mode will be off, that doesn't mean that the balance control is on. And we wrote a new set of conditions so that we would give it a 0 input once the pendulum fell past 165 degrees, so that we didn't get the rotor just chasing the pendulum in circles. And the other thing we did, since we linearized the state space model about the point 0, 0, but our encoder starts with 0, 0 being the downward position of the pendulum, we wrote a new mod function to calculate to convert the angle so that the upright position is corresponds with a pendulum angle of 0 for this part of the model.